Okay, everyone, let's make a start. So today we're going to be talking about moving on from what we covered last week. So last week we very quickly went through Raman spectroscopy, how Raman could be used for different 2D materials, specifically for graphene and MOS2 and also nanotubes and all of the different information that can tell us. And now for the next 3 lectures, so today, tomorrow, and Thursday, we're going to be covering different kinds of energy conversion and storage. So specifically, today we're going to talk about solar cells, how graphene or how different nanomaterials can be integrated into solar cells to improve their performance or to change their design entirely to make use of the sort of unique properties of these different nanomaterials like graphene. So you're probably all familiar with sort of traditional silicon-based solar cells. You've seen these on top of rooftops. How they operate, as you should know, is it's basically an NP junction. So you have some N-doped silicon and you have some P-doped silicon, and you have them in contact with each other. When you have some sunlight, you have a photon hit it, causes a electron-hole pair to be generated. Electron goes one way, hole goes the other. They go round, you complete the circuit, and you get electricity out of it. So these are, of course, mass-produced. These are very, very commercialized. They've been around for 20, 30 years, quite well-established technology. But these are only one way that you can actually use to convert light to electricity. And there are lots of other competing technologies that people are interested in to kind of overcome some of the drawbacks of these silicon ones. One of the biggest drawbacks of these is price. These can be quite expensive. They're very energy consumption. So to actually purify enough high-grade electronics-grade silicon uses a huge amount of electricity to actually produce these. So people look at ways that you can either make flexible ones or lightweight ones or more efficient ones. So this very large table basically plots all of the different solar cell technologies and their efficiency as a function of time. So you can see back in the mid-70s, early 80s, the only technologies that were around were sort of silicon solar cells of different kinds, so crystalline ones, single junction, multi-junction, and thin film. And then you can see how over time how these have got better. So a lot of these technologies essentially flatlined in about the mid-90s and then haven't got much better. And then up here you have sort of the very, very best silicon-based solar cells still, where the efficiency is almost 50%, 46% there in 2017. But I guess the ones that are more interesting for us are these emerging photovoltaics. So these are the ones that are in orange down here. So these are the ones that have only started in the last few years, but their performance is getting much, much faster than other competing technologies. And so we've seen that if this trend continues, these might be able to start overtaking silicon technology. And so the different ones there that you can see are the dye-sensitized solar cells, which is that top one, perovskite solar cells, and organic solar cells, and quantum dot solar cells as well. So we're going to talk in a little bit more detail about 2 kinds of these, the organic solar cells or organic photovoltaics and the dye-sensitized solar cells, and how nanomaterials like graphene can be used to improve them. So just some basics of solar cell testing or solar cell manufacturing. So of course, when you're deploying solar cells or any sort of energy conversion technology using light to make electricity, you want to make sure that you're getting the most out of the wavelengths that are actually hitting it. And so they have these different numbers here. So AM0, AM1, and AM1.5. This is just about how much atmosphere the light has to go through before it hits your solar cells, assuming they're on the surface of the Earth. Ones that are deployed in space use this AM0, and so for ones on satellites, space stations, things like this, they have very different properties or very different things they need to be tuned for. But ones on the surface, of course, we have different absorbance. So visible light, obviously most of that visible light comes through, but then there's absorption due to water vapor in the atmosphere. There's absorption due to CO2, nitrogen, things like this. So those, when you actually look at the spectrum of solar light, you see it's got some certain peaks here, so you basically want to tune them to be very sensitive to visible light, but then you get, if it's very sensitive to certain wavelengths here, you're not even going to detect any of that light. So most solar cells are aiming at the visible spectrum, and that's because the actual irradiance, the amount of power you're getting from it at about 500 nanometers is the best across that spectrum. And so when you're testing these, you'll hear people talk about AM1.5 conditions. That's just saying that it's an average, basically saying how much atmosphere the light has had to go through before it reaches your cell. So of course, if you're right on the equator, the sunlight basically has to pass through the minimum amount of atmosphere, so that's called AM1. So to make it an average, because the Earth is obviously curved and sunlight actually has to go through different amounts of atmosphere before it reaches it, AM1.5 is kind of an average amount of light intensity that actually gets lost by going through. And so that loss can be partly absorbance, but also scattering due to dust particles, pollution, things like this. So AM1.5, if you see that, it just means the intensity of the light at about a 45-degree angle. So solar cell testing normally is done with a solar simulator. So a solar simulator is like this, is a xenon arc lamp. So it can have a very broad spectral wavelength output, and then you use different filters. So you use an AM1.5 filter to basically simulate what that sunlight would be like. That's why it's a solar simulator, not just a lamp. And when you shine light on these and you basically sweep the potential, you get like an IV curve, and you get something that looks like this. So the important parameters you get from a solar cell testing curve like this are the short circuit current, this JSE, or short circuit current density if it's normalized by area. And so that's the maximum amount of current you get when there's no applied potential. The other important parameter is the open circuit voltage, which is down here. So that's the maximum voltage you get when there's no current flowing. And then the power is sort of the most far in this corner as you can get. So if this was an ideal solar cell that was working perfectly, this would be up here. You'd have a perfect square. But what you normally don't have a perfect square because there's some kind of losses. And so what you get is a curve like this, and so that gives you your power, your P max. And so the fill factor here, FF, is basically how close your maximum power is as a ratio of how square it could be. So if this was completely square, if you had a perfect solar cell, so if this is your IV curve, if your solar cell literally went like this, that would be a fill factor of 1. If your solar cell looked something like that, and so the maximum power is essentially there, that's going to be 0.5. So what you want is this to be as close to square as possible, and so that's essentially a metric of how ideal your solar cell behavior is. So here the fill factor is about 0.68 because that maximum power there is 68% of what it could be in terms of an ideal cell. And then of course you can convert the total efficiency. So the efficiency is this formula here, where you just take the short circuit current times the open circuit voltage, which would of course be this position here. You times it by the fill factor, which is basically to get to this P max, and then you divide it by the power in. So that's how much power you were shining on it at the time. So of course, when you're doing a solar cell testing, you set it normally to a fixed amount of incident power, It's normally about 100 watts per square centimetre, but you can change that. And then do your IV curve, get your thing, get your Pmax, and then you get all of these values from the IV curve, and you can calculate your efficiency. So, for example, this cell here is about 7% efficient, which isn't very good, of course. But for some of the cells you'll see that we'll talk about, some of the early graphene ones were much, much less than 1% efficient, so they were quite bad. So that's kind of the basics of solar cell testing. So now we're going to talk about a specific kind of solar cell known as a polymer solar cell, or otherwise known as an organic photovoltaic. So sometimes it's OPV or a PSC, or they're different acronyms, but they all mean the same thing. So polymer solar cells are, as I said, one of these new sort of quite recent solar cell technologies that have been around for a couple of years. And how they actually work is you have a substrate, which is normally some kind of glass or transparent conducting electrode. You have a bottom electrode, you have an electron transport layer, you have an active layer, you have a hole transport layer, and you have a top electrode. And the benefit, of course, is these can all be polymer materials, hence the name polymer solar cell. So these can start to be mechanically flexible. These can be much lighter weight. So if you're talking about putting these on the roofs of buildings or launching these into space, you can reduce the weight of your solar cell by getting rid of that very heavy crystalline silicon and using polymer materials. However, the big problems is they have very low efficiency, so it's only a few percent, and they're also prone to degradation. So normal silicon solar cells last 20, 30 years easily, as long as you clean them every now and then. These ones tend to break down in very strong UV light, again, because they're polymer based. A lot of polymers don't like strong UV light. So lots of people have looked at how graphene can be integrated into this structure, basically in every single part of it. So graphene can replace the electrodes, can replace the transport layers, can replace the active material. So we're going to talk a bit specifically about some examples of what people have done with that. So typically the most widely used polymer solar cells use these two materials, P3HT, which is this polymer here, as an electron donor, and this PCBM, which is a fullerene attached to this kind of short organic chain here, as the electron acceptor. So that's basically your N and P type materials, because you've got one that donates electrons, one that accepts electrons. And so what you do, as I said, in that structure, so you have your two electrodes, and then you have a mixture of this polymer in between. Your donor can donate an electron to your acceptor can donate a hole to your donor. You get your circuit around the outside. Of course, in reality, it doesn't look like this. You get something, this is a much better diagram of it. Normally, when you make these, it's literally just a very big mixture of these two polymers together. So you're not left with a very sharp single interface. You're left with a very large interfacial area, and of course, the larger your interfacial area, the more contact between these two materials, the better your performance will be. And so this is just a better diagram showing again the structure of the P3HT and PCBM, and they're using aluminium in this case as the electrodes. And again, so this is the power, this is the solar cell curve, so here's your short circuit current, open circuit voltage, and so you're getting reasonably square, so it's working reasonably ideally. And as I said, so people have tried to see how they can use basically graphene to replace different components within that sort of traditional polymer solar cell. So of course, the most obvious thing to do with any like nanotubes, graphene, things like this, is simply use them as a transparent conductive electrode. So in these solar cells, you normally have ITO, indium tin oxide, or FTO, which is fluorine-doped tin oxide, on glass. So that's a rigid but optically transparent and conductive layer. Of course, you can replace those with graphene, mechanically flexible but still conductive. So that's what a lot of people have done. And so as I said, so this is a way that you can then make a flexible device, maintaining the transparency of graphene. So this is an example of using a reduced graphene oxide film on PET. So you coat your PET substrate with some RGO, about 16 nanometers thickness. So you've still got, this is quite a few layers thick, and then build a cell out of it. And so this one had a world record efficiency of 0.7%. So that's obviously not very good, but it's still mechanically flexible, and it's kind of a proof of principle that you can replace some of these other materials with graphene to sort of see what you can do. This is another example of using RGO. So you've got your substrate, which is something, in this case it's fixed. You've got your RGO film, your P3HT, PCBM layer, and then you've got your top aluminium. And again, so you can see here, when these are dark, I should say, this curve here, when you do the solar cell measurement, you actually have 4 quadrants that look like this. So when you shine light on it, you might get something that looks like this. So that's your short circuit current, and that's your open circuit voltage, and that's your sort of maximum power. So that's when you're shining light on it. When it's in the dark, you get something that looks, something that looks maybe like this. So basically, you're not getting any current because there's no light shining on it, and so that's what this graph down here is showing. So the red is when there's light shining on it, and the black is when there's no light shining on it. Except they've done it inverse, which is, you can do this thing with the different 4 ones. And so this is with graphene, and this is with the ICO. So you can see that it's basically very straight. So it means there's a lot of resistance. It's not a very good system, but it's kind of working. And so, of course, people took these very low performances, much less than 1%, and thought, how can we improve these and how can we make them better? People still got excited about the idea of making a truly flexible solar cell. So, as I said, using like a film is very cheap, very easy to coat. Take some graphene nanoplatelets and a dispersion, or do some liquid phase exfoliation. Of course, all of those, you're going to have a lot of flake-to-flake contact resistance, so you're never going to get a very good surface. A much better way to do it is use CVD growing graphene. So CVD growing graphene, you have a nice continuous layer. It's going to be optically transparent, and it's going to be much more conductive. So here they've grown multi-layer graphene on some nickel by CVD, and so they're getting an optical transparency around 85%, and they're getting a sheet resistance of around 374 ohms per square, which is quite good. And then so this is how they've got their substrate with their graphene layers on it. They put their PDOT PSS layer on it. They put another conductive polymer on top of that, and then they're putting their top aluminium. And so you can see the performance here again. ITO in the blue looks quite nice, and then the ITO in the dark is down there. And then with the graphene layer, it looks like this. So it's much, you can see compared to here, where it's basically very, very straight, very low fill factor. It's going to be very, very low efficiency. Here, the fill factor is much better. It's starting to look a bit more curved. Still pretty far from where it should be to be ideal in the square, but it's a big improvement from those RGO films. And so here they're getting an efficiency of around almost 1.2%. So it's a big improvement to use CVD graphene to replace ICO. As I said, you can use this to make it flexible. So this is another example of using a CVD graphene on polyimide substrates. So they've got their polyimide, they've got a thin metal layer, usually aluminium, and they've got their P3HT layer, and then graphene on the top. And so in this case, the graphene was just the top electrode, and they were able to get efficiencies around 3.2%, so it's quite a big improvement. So here they were looking at the different metals and how basically you can change the energy levels of the different components to try and maximize this fill factor. And so it was found that one of the reasons that this performance was much better, as I said, that the degradation that you get in a lot of these polymer solar cells is that they fall apart over time. And part of that is oxygen getting into them. So I think you've talked about this before, about that graphene is quite impermeable to a lot of gases, especially if you have no defects in it. So by having this sort of graphene layer as the top gate in the solar cell, you also stop air diffusing into it and oxidizing it and lowering its performance. So having this graphene layer on it actually encapsulates the whole solar cell, and that increased the stability and made it last much, much longer. So that was an example of using graphene not just as a transparent conductive electrode, but using it as a barrier film to actually encapsulate your cell. Sorry, before we move on, any questions on using graphene as a transparent conductive electrode? No? All clear? As I said, so it's pretty simple, that obviously you know that if you have a film where you've got lots of flakes or lots of lots of particles in contact with each other, the resistance is always going to be much higher than if you have a CVD growing continuous film. So there's always benefits of using CVD, but you can still maintain that mechanical flexibility with that conductivity. So moving on, so as we said, that you can use graphene or other nanomaterials as the electrode. You can also actually use them as the charge extraction layers, so the hole transport or the electron transport layers, or the hole extraction layer, they call them, it's the same thing. So in this case, what you have is you have a standard ITO as your substrate or as your transparent substrate. You have a layer of, say, graphene oxide or some kind of other graphene material next to your P3HD. So if you actually plot the energy levels of these next to each other, of course, graphene oxide, unlike graphene, which has no band gap, if you oxidize graphene enough, you start to introduce a band gap and either make it completely insulating, as it normally is, or you can shoot it and make it a semiconductor, but with a much lower conductivity. And so you can use this level of oxidation to kind of use the GEO to extract charge from your active material, your P3HD, PCBM. And so by changing how oxidized this is, you change where energy levels sit in relation to the active materials in the aluminium. And so you can see here, so this was using a graphene oxide which had a work function around 4.9 eV. So I think completely oxidized, the band gap is around 6 or something. So this is fairly highly oxidized, but you can still use a to match the energy levels. And so here you can see the IV curve of the dotted line there is ITO only, and then here they've got graphene oxide replacing what P.PSS is the polymer they normally use for this whole extraction layer. So the GEO here is replacing P.PSS, which is a conductive polymer. So you can see there's basically no difference in performance. So the GEO is 2 nanometers of GEO is working as well as this sort of macroscopic layer of polymer. So that's quite good. That's the energy level of the P.PSS there in relation to the GEO. So you basically can replace this polymer with GEO and get equivalent performance. So it's about 3.6%, which is quite good, and much higher than having no extraction layer. So if you just have P3 HT PCBM graphene or your metal, you'll get an efficiency about 1.8. But if you have this barrier layer basically to match the energy levels of the active material, you get much better performance. So that's why you need this additional hole extraction or electron extraction layers in between those samples. Again, this is another example of instead of replacing the hole extraction this time, so instead of replacing the electron extraction, now it's the hole extraction. So again, this is using GEO. So this is using a GEO film that's been thermally annealed at different temperatures. As you anneal it, you reduce it, and you basically go back to a more conductive or more like graphene material. And so here you have the black is where there's no hole transport layer, so quite bad performance. P.PSS is the standard one, which is the red. Graphene oxide just as deposited in the green there, and then as you anneal it slightly, you increase the conductivity because you're getting rid of some of those oxygen functionalities, and you're getting better and better. And so then up to a few hundred degrees, which is quite low, you're basically again able to reproduce the performance of that P.PSS that you've replaced. So you've still got a much thinner layer, you're getting much more light through it, which means you're going to get much more efficiency. And again, so these are up to about 4%, which is, okay, it's only slightly better than the sort of traditional polymer, which is 3.85%. So again, it's just showing how graphene oxide can replace that traditionally used material to improve the performance. Any questions on that? So again, with that one, with the different, as we go through the different components, obviously with the transparent conductive electrodes, it's obvious that you just need something transparent, optically transparent as much as possible and conductive. With the hole extraction, electron extraction layers, it's all about matching the energy levels to the active layers. So if you're going to be using the same P3HT, PCBM active layers, you need to kind of tune the band gap of whatever your material is. And so one of the benefits of graphene oxide is that you can tune its band gap by thermally annealing it, changing the amount of oxygen functionalization on it. Okay, so that's the next sort of the part is actually using the graphene material as the active layer itself. So actually using the graphene as the the solar part. And so, as I said, fullerenes are what is normally used. The PCBM contains a fullerene, and that's because they're basically very good electron acceptors. They're very strongly p-type doped, accept electrons very easily. And so in 2008 was the first use of using graphene. So in this case, they've replaced the fullerene component with a graphene. So they've actually chemically functionalized graphene, similar to the way that the fullerene had this organic group attached to it. They've now got graphene with an organic group attached to it. Basically, the performance was pretty bad. So here is the IV curve with different annealing temperatures. And even at the best one, it's still not very square. It still doesn't work very well. So the efficiency was only about 1.4%. But it was an example of how you could replace fullerenes with graphene, possibly showing some promise of how they could be used. Then lots of people did lots of work to try and improve that. So here was chemically grafting this polymer, the P3HT, onto graphene. And so this is graphene, P3HT, and C60. So they've now got basically 3 components. And so here they're getting efficiency of about 0.6%, which isn't good, but it's about a 200% improvement compared to not having the graphene in there. So having the graphene in there makes it more conductive, a bit like adding it to a conductive polymer. Sorry, adding it to an insulating polymer. You can make it conductive by having graphene in there. And so you can improve the performance of your solar cell by having these conductive additives in there. This is another example of that. Again, so this is chemically grafting. In this case, the fullerenes, the C60, onto the RGO. So this time you've got a sheet of your RGO and you're attaching some fullerenes to it. And so compared to a cell with only C60, which is about 0.4%, which is one of these, and then you get a 2.5 times increase by having the graphene covalently attached to it. So this is the one down here. So by basically chemically attaching or otherwise just dispersing graphene in there with your active material, you make it more conductive, which improves your solar cell efficiency because you're able to basically get more of your excitons out of your system. So another way to do it is to, as I said, introduce a band gap. And so people have done that through oxidation, just by making GO. Other way you can do that is by nitrogen doping or boron doping. So nitrogen doping of graphene is a very popular way to improve its increase its band gap from nothing to something. And so people have used, as I said, nitrogen and boron are the 2 most common ones. So this work here is an example of using a P3HT PCM solar cell with nitrogen doped graphene as the actual active layer. So they take GO, they reduce it in an ammonia atmosphere, and basically the ammonia decomposes and then starts to introduce nitrogen into the structure. Nitrogen is quite good as a dopant because it can obviously make 3 bonds, so it can fit into the actual plane of graphene without causing too much disruption. So you can have it either substitutionally bonded to 3 carbons, or you can have kind of a dangling nitrogen stuck in the system. And then here they've just basically got a mixture. So you've got your P3HT and your PCBM polymer, and then this nitrogen doped graphene is all mixed through the structure. So it's basically just as an additive to basically either improve the conductivity, but also tune the band gap of that active layer. So they were able to get an increase of 40% in the efficiency. Without graphene, it was 3.2%. With this nitrogen-doped graphene, it was up to 4.5%. So just by adding a very small amount of this N-doped graphene, we're able to improve the performance by quite a large amount, which is quite good. Another way to do it is, so you've heard of graphene quantum dots, yes or no? Yes? I mean, graphene quantum dots are very similar to sort of the standard quantum dots, so like semiconductor quantum dots, cadmium selenide, lead sulfide, things like this. In the case of graphene, you basically take your sheet of graphene, which is continuous, has no band gap, and you start to make it confined, so you break it up into very, very small pieces. Once the sort of diameter of your graphene gets below about a nanometer, it starts to have a band gap due to this quantum confinement. And so lots of people have been looking at ways to take carbon nanotubes, unzip them, and then break them up into very small fragments of graphene quantum dots. And so these, the band gap is usually quite small, but if you can tune them or functionalize them. So here they've taken GO, they're smashing it up basically, oxidizing it into oxidized quantum dots, reducing it or functionalizing it to kind of again have more control over this band gap and be able to tune the wavelengths that it's sensitive to. So again, they're adding these graphene quantum dots as an additive into a sort of traditional P3HT PCBM solar cell. And so you can see in black here is the reference. So this is without any graphene quantum dots. And then they've got the three different kinds here, the GO, the partially reduced, and the fully reduced. And all three of those are improving the performance slightly. Not very much, but now the efficiency is up to sort of 5.2%. So if you imagine, we talked at the very start about the very first graphene additives, the efficiency was less than 0.1, it was 0.2, 0.3. And so now, a few years ago, we're now up to 5.2%. So that's why we're talking about this very rapid increase in performance of these polymer solar cells when you add graphene to them compared to other technologies. So that's polymer solar cells. So that's showing how standard ones work, and then how you can replace the ITO layers with graphene, how you can replace the hole and electron transport layers with graphene, or how you can replace the actual active material. So each one of the components within that cell can be replaced by graphene. Are there any questions? Yeah.
Why the nitrogen filled graphene can perform as your receptor? I think it should more perform like a donor because you get 5 electrons.
Yeah, so it depends on how defective the graphene was when you first doped it. So normally nitrogen doping, as you said, increases the electron density and makes it N-type, makes it an electron donator. But if you've got, depending on where the energy levels of the other materials are next to it, so if this is your 2 electrodes, and this is your, say this is the energy level of your N-doped graphene, so normally you'd say, okay, this can donate an electron, but if your P3HT PCBM energy level is higher than this, it's still going to be an acceptor, even though it's slightly more N-doped. So it's where its energy level sits relative to the active material. But yeah, normally people N-dope to make it a donator and boron dope it to make an acceptor, but as I say, it depends on what else is in the system with it. Any other questions on the polymer solar cells? No? Okay, so we'll move on to the second kind of solar cell that we're going to talk about, which is the dye-sensitized solar cells. So who here knows about dye-sensitized solar cells? Anyone? No one? No? Okay. They used to be very, very popular and have been around for a while. How they work, so sometimes they're called artificial photosynthesis because they work a bit similar to the way that chlorophyll works in plants. So these are, again, photoelectrochemical systems, so they convert light to electricity, but they do this using more a chemical process, so there's not an NP junction, it's not a semiconductor device. These were first produced in the late 80s by these guys, Brian O'Regan and Michael Gratzel. So Gratzel has published, I don't know, thousands and thousands of papers on these. So because of that, they're sometimes called Gratzel cells, because he was the first one to discover them. And so how they work is quite simple. So you have, again, 2 transparent conductive electrodes. So this can be FTO, ITO, some kind of glass. And then you cover it in titania nanoparticles. So this gives you a very high surface area semiconductor material. This is then coated in a dye, hence the dye sensitized. And so this dye is something that can absorb light in the visible spectrum and then donate an electron. And then you have an electrolyte. So this is all in a liquid. So this contains a redox couple, so it's an iodide, triiodide. You have these 2 ions floating around. And then you have a very thin layer of platinum coated on the counter electrode. So light comes in, passes through the transparent conductor, hits the dye, and excites it. So this is your dye layer here. And so light comes in, electron goes up, donates it to the titania. It goes through your cell, comes back to the platinum, and then this iodide, triiodide basically shuttles the electron and reduces the dye back down, and that's how you get your complete system. So electron flows through the external circuit, comes back into the cell, and electron transports it back. So the electron basically comes in, so it's generated in the die, transports through the titania, through the cell, back, through the platinum, and back in. So these were quite popular for a long time because it was kind of a completely different way to generate electricity that didn't require any semiconductor, high-end silicon or any materials like this. So, of course, with graphene, lots of people are very interested in how graphene can make these better. So people have looked at adding graphene or other 2D materials to every single component within it. So, of course, as we've already covered, replacing the ITO with graphene as the transparent electrode, replacing the die with graphene quantum dots as the actual semiconductor layer, replacing the titania with graphene as the semiconducting layer, adding graphene to the electrolyte, because why not? Adding graphene to the cathode to replace the platinum, you name it. So basically every single component of this cell, people have looked at can it be made better by adding graphene. Some of them, yes, some of them less so. So the transparent electrodes, sensitizers, and cathodes are the three kind of most promising ones that we'll talk about in a bit more detail. So you will have covered previously all of the different ways to produce graphene, as we've already said. So pristine graphene, as you know, up here has very high conductivity, low oxygen content, and is very high mobility. As you basically increase the amount of defects or reduce the crystallinity, you basically get down here to amorphous carbon. And then as you increase the oxygen content, you come out here to GO. And so you have kind of different methods to get within this kind of three parameters. So you have, if you start with GO and you reduce it, you can get something kind of in the middle here where you're nowhere near as conductive as pristine graphene, but you're a bit better than GO. Same with thermal. Thermal reduction normally has a bit more defects. And so you kind of have this different parameter space that you can look at to get the kind of graphene that you want. And so each production method, as you know, has different conductivity due to its flake size, functionality, and things like this, and also oxygen ratio. So the less oxygen you have, the more conductive it is. So again, for all of these applications, it's all about choosing the right kind of graphene. So mechanical or liquid exfoliation can usually be quite pristine. Electrochemical exfoliation is also not bad. CVD, depending on domain size, again, quite good. So for a lot of these, it all depends on how you make your graphene. So just like we said with the polymer solar cells, lots of people have looked at CVD or other different methods of looking at graphene for transparent conductive electrodes. CVD is one of of course, the best ones. So these black squares here are CVD grown graphene. So very high transparency because it's very thin. You only have a few layers. So you can get about 90% transparencies and a sheet resistance of sort of 10 or even less than 10 ohms per square. So this dotted line here is the minimum it needs to be commercializable. And this solid line here is highly doped. So you can dope your graphene, make it more conductive without really affecting its transparency. So that's what this sort of green triangle square is here, saying, okay, now we're getting much better than sort of the industry standard. You can see out here where you've got RGO and liquid exfoliated graphene. The transparency is normally much less. It's a thicker layer. It's macroscopic. You normally have tens of nanometers of it. And the sheet resistance is much higher because, again, lots of flake-to-flake contact resistance. So it's all about, as I said, tuning the right production method for the right application. And so just like we saw with graphene quantum dots for the polymer solar cells, you can actually, in your dye-sensitized solar cell, you can replace the dye with a graphene quantum dot. So this is an example of one that's then been passivated with some organic molecules around it. So they normally range in the size about 1 to 30 nanometers, so they're very small. They normally have a maximum absorption of about 600 nanometers, and this is their absorption coefficient, which is so this N719 is one of the standard dyes that is used in dye-sensitized solar cells. So these graphene quantum dots actually have a much higher absorbance coefficient, means they can absorb more of that light, which is why they're kind of interesting. And so lots of people have looked at incorporating these into solar cells, but as I said, so far the efficiency is quite low, 0.06%. So it's basically literally anything else would be better almost. So you can see the photocurrent is quite square. You're getting very nice ideal behavior, but this is 200 microamps per square centimeter. So yeah, the efficiency is very poor still. But as kind of a fundamental exercise, it's quite interesting to then look at how these graphene quantum dots are aligned. Are they all packed flat side to side? Are they sitting on their edge? Things like this. So one of the ways that people have done to try and improve this performance is control how they actually sit in their surface, and then how they functionalize and how they interact with each other. And so this is an example of replacing that counter electrode. So traditional ones use platinum nanoparticles as a counter electrode to this iodide triiodide couple. Obviously platinum's expensive, it's a metal, it's not very flexible. Lots of people have looked at replacing it with carbon nanotubes for a long time, and then more recently graphene or doped graphene. And so of course replacing platinum would be very nice, and then you can basically get quite good performance out of this. So this dashed line here is what the performance of that solar cell looks like with platinum. And then if you replace that platinum layer with this functionalized graphene, you can almost get the exact same performance out of it. And so this is Geo with some different, I can't remember which functionalities this has in it. And so you're basically not losing any, you're losing 0.5%, it goes from 5.5 down to 5. So the fill factor there is the same, and the efficiency is very, very close. So that's a good example of how replacing platinum, which is obviously very expensive, with a much cheaper material like Geo can basically get you almost equivalent performance. And so the reason it works as a catalyst is all of these edge sites. So in the case of the flake, you've got lots of defects, you've got lots of edges. All of these oxygen-containing functional groups and edges are very catalytically active. So that's where your chemistry can happen. So the more surface area you have of your flake, the more catalytically active you'll get. And so you can start to even get as good as performance as platinum, which is kind of the best catalyst you can get. So, summarizing. So we've covered polymer solar cells. We saw how graphene and different nanomaterials could be used as each component, the transparent electrode, the hole and electron transport layers, and the active material themselves, as long as you introduce band gap. And then in dye-sensitized solar cells, again, people have tried to replace every single component with graphene, transparent conductive electrodes, the sensitizer as the active material, and then as the counter electrode themselves. And so you basically should be able to see that, I mean, we're focused on graphene here, but of course you can use other 2D materials like MOS2 as a semiconductor would be ideal as a sensitizer. Lots of people have used these heterostructures of graphene and semiconductor materials to make photodetectors or solar cells. One of the benefits of the carbon-based materials is they're much cheaper. So we can produce graphene or graphene oxide at very, very large scale quite cheaply, which makes it integrating that into solar cells quite easy. Questions?
Graphene quantum dots probably have some defects on the edge.
That's right, yep.
Yeah. How to reduce it or?
So normally you can passivate them with something. So in this case, you have this organic molecule here is basically wrapping around the edges and passivating them, because these edges really want to stick to each other, or they either want to react with each other. So what you don't want to do is the graphene quantum dots to stack on top of each other, because then you're basically going to lose that quantum confinement, and you're not going to have a band gap anymore. So you need to make sure your quantum dots stay dispersed. So if you've got, this is one quantum dot here, you need to put some kind of organic molecules around it to make sure that these don't come in contact with each other, because otherwise, if these just stack on top of each other like this, you're basically going to make a very small piece of graphite. You're not going to have any band gap. So that's one way to passivate them, but this passivating with an organic molecule also prevents any edge defects here reacting. So if you have something there stopping, if these two defects would come together, they might covalently attach or otherwise react. But normally, depending on how you make them, if you're making this in solution, they're passivated by oxygen groups or whatever's in that solution, or if it's by CVD, you've got some hydrogen passivation on them as well. So you can't really prevent those edge sites. You can just make sure that they've reacted with something before you stick them together.
the exam, do we just need to know like the materials and the general concepts employed? Or?
It'd be basically the same. Well, you would remember. So in the third year nano exam, for example, the sort of questions I like to ask might be, oops, go forward. So that one. So how can graphene improve performance of a dye-sensitized solar cell?
Yeah.
Tell me one way. So you might say, oh, graphene could replace the ITO as the transparent conductive electrode, but it would depend on the way you make the graphene. It has to be, high optical transparency, high conductivity, and so to do that, I'll need to make sure I choose a graphene production method like CVD, etc., etc. So normally I guess the only at the very start, the thing that's important to know is this sort of basics of how to calculate efficiency. So knowing that it's the short circuit current times the open circuit voltage times the fill factor to get the power that's generating divided by the powering to get the overall efficiency.
Thanks. With specific things like the polymers, would it be okay to remember them as PCBM?
Absolutely, because I don't even remember what their full name is.
No.
Any other questions? No? If not, I'll see you tomorrow. You basically getting rid of some of those extreme functionalities and making it more conductive.
But here it says
So geo, like pure geo, is completely insulated, and completely reduced RGO it's not as conductive as graphene, but it's much higher conductivity. So as you increase the temperature and reduce it more and more, get rid of more of that, it gets more and more conductive. That's why performance is getting better and better and better as you increase the conductivity. Yeah. That's right.
and the totally reduced the graphene side is
Yeah, well, so there's kind of a trade-off between, of course, if you have say this is your and this
This is ready-made drives.
and then say this is at 350.
Yeah.
But then if you start to increase it too much, it might start to
And I'm not actually. I've got massage.
Oh God, is that finally?
Yeah, you might have you might still need 5%. So your oxygen is going down, but the conductivity will So this is GO. This is CPO.
Where you go?
No, we go space rooms.
This has more defects. Here the oxygen is passive.
Yeah, let's finish the booster.
Yeah, this one is basically very defective. So here you have lots and lots of here, as you start to remove those, you actually end up with a revolving bond. Here, where it's completely reduced, you get all of the oxygen. Now you've got
Paper introduced a material optimization approach that tried to get the contact.
lots of defects. So now these defects size it's reducing.
Possibly.
So because you've got nothing to passivate, it's trying to replace our oxygen. So, this is probably an over-exaggeration of how it works, but that's why the performance gets better. And if you keep going to higher and higher, it will start to get worse. But even annealing in air, you'll reduce the oxygen content. Eventually, you go too high, you just start to oxidize it again. So that's more like 550, 350 is just
For the average version,
Yep.
we test it in the dark.
Yep.
There is also occurring.
Yep, that's right. Yep. So that's just basically to do with the conductivity of it. So if you actually look at all four quadrants, it looks something like this. And this one looks like this. So this is your current. This is your voltage. So here, in this quadrant here, you've got this is your photocurrent. So this is all of the current that's generated by that light. Here, we have this is your electrode, and this is your electrode, and this is your material. So when you shine light on it, an electron goes here, down here, through your cell, and then down there. So that's what's happening in this quadrant. Of course, if there's no light shining on it, but you're still applying a very large potential, you're still starting to shift these levels. So what you can actually do is when there's no light on it, you can then start to have negative current because the current's flowing the other way. So now, if we shift this level up here, this is coming into here, it's going into there, it's going into there. So going through this circuit back there. So you've got, in the dark, you have the reverse process.
So it's also because the applied potential make this.
Exactly, yeah. So as you apply the potential, you're changing how easy it is for this to happen. So when there's very low potential, it just happens normally. At very high potential, you get to the point where these levels are basically equal. So there's no transfer between there. So that's why there's no current. But then as you keep on pushing this more and more, you start to get negative current because now it's flowing in the opposite direction. So when it's dark, it's always in the current direction. But this gives you an idea of the ratio of this position to this position, of how optimized your energy levels are in your system. So you want this to be, in the dark, you want this to be zero or very close to zero. Sometimes it's not, sometimes you get a little bit of current like this. And that's bad, because that means that this is basically wasted current. You're not generating this, because this is current flowing in the wrong direction. So the total current you're getting is less, because you're losing current. So in the dark, you want it to be zero.